What up? This is the Unit 3 review. It's 43 questions, so we got to get to it. We start you off with a table problem, which you saw in the lesson 4 homework, which you're going to see on the test, which is testing you more on your theorem knowledge than anything. Why is that testing you on your theorem knowledge? Like, if I read the question, let's read the question. It says, which of the following must means always be true? And if you plot the points, you got -1, -30, 0, -2. This isn't to scale, but who cares? 3, 10, 5, 18. Like you could see, maybe it looks like the function would be increasing concave down. Not necessarily. You don't know that you're connecting these smoothly like that. You could be going like this through the points. Okay, and it's important to keep in mind that you don't know what happens in between points. So if you're told, hey, f has no critical points, well, so not necessarily. I got a bunch of critical points if I draw my function like this. F prime is positive, which means f is going up for all the intervals. Well, it's like it could be, but must it be? No, must not be. So the second derivative negative is f concave down or f prime decreasing. No, it doesn't have to be. Like here, we're concave down, concave up. Okay. But we look at this, f prime must equal 8. And 8.
That's why I was. Oops.
You're good. And this is testing you on your knowledge of the mean value theorem. And it's good to start with this because after all of the function analysis we've done, we forget about the mean value theorem we learned in lesson 1. Mean value theorem says if you have 2 points, point here, point there, you connect these points with a secant line, find the slope, you're guaranteed to have at least one location here. I'm going to have many where your tangent slope equals that secant slope. So let's calculate the secant slope. The secant slope is just using the slope formula. 18 minus -30 over 5 minus -1, and I get 48 over 6, which is 8. So we are guaranteed by the mean value theorem to have a tangent slope equal to that secant slope, that average rate of change, instantaneous rate of change equaling our average rate of change, which is 8. So yes, this must be true. See, is there another option? Graph has no points of inflection. Yeah, no, I could have lots of points of inflection. So it's just going to be B. That is must be true. It's a theorem. There, B. Okay. Number 2. We got a polynomial function. We got x coordinates of a and b, both equaling y coordinates of 1. What must be true? It's a mean value theorem question, no matter how I connect it. Now, one thing that I forgot to mention, it's like they talked about being twice differentiable. Twice differentiable just means, like, think of it as a polynomial where you can take the derivative twice. It has tangent slopes and it has second derivatives everywhere. So twice differentiable doesn't mean this is like the second derivative or anything. It's just like I can take the derivative twice. So it's like very much differentiable. Mean value theorem works for differentiable functions. This polynomial function with a degree greater than 2, that means I can take the derivative twice. We're differentiable. So this is like we can connect these points. However we connect these points, it has to be smoothly. The secant slope is 0. I'm guaranteed to have a tangent slope that equals that secant slope, which is 0. Must our second derivative be 0? No. Must we have a y coordinate equal to 0? No. I mean, we could, but must we? No. So mean value theorem must. Can't change the problem. Computer froze. There we go. All right, mean value theorem question again. We're guaranteed to have a tangent slope that equals my secant slope. This is the setup for the mean value theorem, really, like this. My derivative When will my tangent slope generator generate? Let's find the slope. I'll need the 2 points, so I have to plug in 3. I get 27 minus 27, which is 0. And I plug in 0, I get 0. That's nice. So my secant slope 0 minus 0 over 3 minus 0, which is just 0. So this really is like, when do we have a horizontal tangent location? Factor out and 3x, I get x minus 2. Solutions are 0 and 2. Mean value theorem guarantees to have a solution inside your interval. If they put 0 and 2, I would want to maybe select that, but they wouldn't put 0 and 2 and then just 2. So I'm just selecting 2. Let's double check. 3, 9, 27. 3 times 9 is 27. So that's good. Another mean value theorem. It's like, oh, they didn't give me an interval. Yeah, they gave me an interval right there. Pi over 2 to 3 pi over 2. So like the bottom is going to be 3 pi over 2 minus pi over 2. Then I need the top. I'm going to plug in 3 pi over 2. That's 3 pi over 2 divided by 2, which turns into the sine of 3 pi over 4. Sine of 3 pi over 2 is positive. Sorry, 3 pi over 4 is positive root 2 over 2. We're over here. Sine value is positive. And then pi over 2 turns into the sine of pi over 4, which also is root 2 over 2. We're over here. Sine positive root 2 over 2. So it's another nice situation where the secant slope actually equals 0. I don't have to worry about the denominator being pi. It's 0 divided by pi, which is 0. Now I just need to find when the derivative is going to produce that. I got to do the derivative correctly. It is a chain. We've probably forgotten about the chain rule. We haven't done it much. X over 2 can be written as 1/2 times x. Its derivative is 1/2. The outside's derivative is cosine. So the correct f prime is cosine x over 2 times 1/2. And when does that equal 0? Fortunately, this 1/2 is not going to make any difference. Like, I'm going to multiply both sides by 2 and it's gone. I just need to figure out when cosine equals 0. So maybe this is easiest to just like figure out, well, like cosine of pi over 2 and cosine of 3 pi over 2. So x could be pi or x could be 3 pi. The one value between pi over 2 and 3 pi over 2 is pi. So that's that one. All right, so good mean value theorem practice to remind ourselves of that lesson 1. This is the same thing. Interval, instantaneous rate of change, average rate of change. When will my tangent slope generator generate this specific tangent slope, the secant slope over my interval? Hopefully we won't get 0 here. I don't think we will. 27 plus 15. I think this was a test question from last test. Is 42. Plug in 1. I get 6. So I get 42 minus 6 over 3 minus 1. 42 minus 6 is 36 over 2, which is 18. When will my tangent slope generator generate a slope of 18? It's my derivative, f prime. Subtract 5, I get 13. Divide by 3, I get 13 over 3. Square root, I get plus or minus root 13 over 3. The positive root 13 over 3 is between 1 and 3. Mean value theorem, mean value theorem, mean value theorem. I mean, I could do this problem again, but it's just the same as the last problem. So, like, I'm not going to show you how to do it. It's the same thing as what we just did. So if you have any issues with this problem, let me know. But you should be able to calculate it yourself, get the answer. Derivative equal to secant slope, average rate of change. Slope of a tangent equaling slope of a secant. Okay. All right, this is more graphical representation of the mean value theorem. You're given a graph of f, interval from -4. Find the point at -4 to 3 by the point at 3. Sketch the secant slope so that you see, like, what is the slope at some negative number. how many values of x satisfy the conclusion? So like how many locations will our tangent slopes be parallel to or equal to the secant slope? And I see there's 3 locations. Okay, mean value theorem, mean value theorem, mean value. A lot of mean value theorem. You will have some mean value theorems. Fun! Critical points. Critical points are when the derivative equals 0 or undefined. They are possible max-min locations. Don't look at the second derivative. Critical points are just with the first derivative. Don't do a sign analysis, okay? Don't do a sign analysis. You don't have to. You're not asked about relative extrema. You're just asked for critical points. So you just take your derivative, set it equal to 0, solve, and then that's it. Now, unfortunately, when I take this derivative, I got to do some work here. It's a product. It's a first times a second, so that means I have to use the product rule. And when I take the derivative, I have to use the chain rule. However, I'm just going to do this for one of them, for the first one, the first derivative. However, since the inside is just like x plus or x minus, the derivative of the inside is just 1. So I really just worry about the derivative of the outside. So if I take the derivative of the first, it's like 5, leave the stuff in the middle, to the fourth, times 1. Doesn't change it. Times the second, plus the derivative of the second, 4 stuff cubed, times 1, but I don't have to worry about it, times the first. To solve this equal to 0, we should factor, okay? We don't like sums, factoring things. Though I can just see like 3 and negative 2, but like, let's just make sure. Maybe there's another one. So I'm going to write this as 5, like a to the fourth, b to the fourth, and this is 4b cubed, a to the fifth. So I could take out 4 a's, 3 b's, and that's it. And what's left over is 5b plus 4a. That's probably going to give me a third critical point. So a to the fourth is x plus 2 to the fourth. B cubed is x minus 3 cubed. I have 5 b's. I have 4 a's. I'm going to simplify the inside here. This is 5x minus 15. This is 4x minus 12. Combining everything, I have 9 x's minus 27. Wait. I messed up. B is x minus 3. A is x plus 2. I thought that looked right. I thought that looked wrong. So 4x plus 2 is 4x plus 8. Simplify that. It's 9x minus 7. So now that it's factored, I have solutions of negative 2, 3. That makes the first 2 pieces 0 of my product. And the last piece, I'm going to have positive 7 ninths. If I plugged in 7 ninths into this derivative, I get 0, which is fascinating. Means I have 3 critical points. Tricky problem to figure out. Good practice of derivative rules, factoring, solving. G is differentiable, cool. G is increasing. On what intervals is G of x cubed minus 6x squared increasing? So this is going to be increasing when its derivative, y prime, is positive. Okay, if G is increasing, that's telling me G prime is positive. Right, this is the table that we've put together. But this is not just G, this is G of stuff. So it's like, when is the entire thing positive? So I got to take the derivative of this guy, G of, and then x cubed minus 6x squared. And the derivative of it, and this is good chain rule practice, y prime is g prime of whatever was on the inside times 3x squared minus 12x. And the question is, when is this positive? Well, to find when it's positive, you find when it's zero, you do a sign analysis, okay? Now, here's the ticket here. G is increasing. G prime is positive. This is positive. G prime of this. This could change signs. So what I'm going to do is actually factor out a 3x from this guy, and my sign analysis will be around 0 and 4 when this piece could be 0. And these will be the signs of y prime, which will tell me when y is increasing or decreasing. Now again, g prime is always positive because g is increasing. So this is positive, positive times a positive times a positive. Plug in 2, positive, positive, negative. Plug in -1, positive, negative, negative. That means y is increasing, decreasing, increasing. When is y increasing? X is less than 0 and x is bigger than 4. That's this one. This is a tricky problem. Again, we're kind of been testing you on the chain rule a little bit here. You had some homework problems involving the chain rule. You didn't have many quiz questions that involve the chain rule. So maybe that's something to think about. The fact that I didn't put too many quiz questions on the chain rule for your test. But this is good practice anyways, conceptually understanding things. All right, this is more like the problems that we're used to. Here's the function. One is f increasing. So f is going to be going up when f prime is going to be positive. We need to do a sign chart analysis of f prime, figure out when f prime is positive. F prime is 300 minus 3x squared. I'll set that equal to 0. See when it's undefined. I don't have to worry about the undefined part because there's no denominator. Subtract 300 or factor out really a 3, really. And you can kind of see like this is plus or minus 10, or you could factor this as 10 minus x, 10 plus x. It's up to you. It doesn't matter if you factor or if you just solve normally. You should get -10 and +10. These are your critical points for f. That's when f prime is 0. If I plugged in something like 12, it's 3 times a negative times a positive. So that's a negative. Multiplicities are 1, so the signs will change. Telling me f is going down, going up, going down. F is increasing when f prime is positive. F prime is positive between -10 and 10. Bummer. It shifted on me. Should like this over. Question, are we on 10? Yeah, there we go. I can't move it. Let's go to 11. When is f decreasing? Okay, so now I'm looking for when f is going down. That's when f prime is negative. So sign analysis of our derivative is going to help this. I already have f prime. Make sure you know what you have. Pay attention. So I need to take this, see when this is 0 or undefined. This is important. X equals 0 is a critical point. That's when my denominator of this equals 0. If I plugged in 0, f prime of 0 would be 0 minus 2 over 0, which is undefined. So putting down x equals 0, that's important. Now solving this equation set equal to 0, I don't know. I'm probably going to move the 2 over x over, multiply both sides by x, and I get x cubed equals 2, which means x is equal to the cubed root of 2. I don't need a plus or minus because it's an odd root. The cubed root of 8 is 2. The cubed root of -8 is -2. There's no plus or minus. So I do have 0, and I have the cubed root of 2 as f prime zeros. Sorry, this is a 0. This is undefined. Now I'm going to go into this. I don't have it simplified, so I've just got to plug in, and this is not 3 root 2, this is the cube root of 2. I'm just going to plug in values into that. I might have to do a little bit of conceptual thought about it. Start with something big like 10. 10 squared minus 2 over 10, obviously. That's going to be positive. 10 squared is 100 minus 2 over 10. The cubed root of 2, I mean, I don't know what that number is. So I'm just going to go a little bit to the right of 0, like 0.0001. Okay? If I do 0.001 squared, very, very small, minus 2 divided by 0.0001, that's going to be a very big number. 2 divided by 0.001 is like 200 or 2,000. So like small number minus very big number, it's going to be a negative. If I go to negative 1 squared, positive. 2 divided by a negative is a negative, but I'm subtracting a negative. So this turns into a positive. So I have a positive plus a positive. That's a positive. When is f decreasing from 0 to the cubed root of 2? It's a good question. 12. All right, all the answers are all about f increasing, decreasing. So let's do our f prime sign analysis to figure out when f is going up or down. Got to figure out positives and negatives, find the zeros. So f prime, 3x squared plus 12. When does that equal 0 or undefined? Don't have to worry about it. You can factor out 3 if you want to. That is a good problem too. A lot of people are like, all right, sweet, negative 2, positive 2. No, no, no. There are no real solutions for this. You'd have to do the square root of a negative number so that you'd get a 0. No matter what I plug in for x, whether it's a positive number or a negative number, squaring it becomes a positive times 3 stays positive, add 12. Turns out f prime signs are positive everywhere. They never equal 0, which means f is increasing everywhere. C. Good question. Making sure you understand like when you can't solve. Sometimes like you can't factor. Sometimes you can't solve. Sometimes your signs are the same. Always. All right. This is more like a question you saw on a quiz. This is definitely a question you'd see on your tests. You're given f prime. That's important. You figure out when f has a max. So what you're looking for is when f prime changes from positive to negative, because that means f is going to be going up, then going down. Okay, so I need to throw down f prime, find its zeros, which are at 0, 3, and negative 1. I'm already given f prime. I don't have to take a derivative or anything. So negative 1, 0, and 3. Do a sign analysis, maybe use multiplicities, maybe just test your intervals. It's up to you. See the multiplicity of 3 is 2. That means you're not going to change signs at 3, but you will change signs at negative 1 and 0. So let's start over here on the right, like 5, positive, 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 positive. Don't change signs at 3. Change signs at 0. Change signs at negative 1. That means f's going up, going down, going up, flattening out, going up. We only have one max. X equals negative 1 is the only relative maxima. So just that, okay? Make sure you get your sign analysis right. If you don't understand multiplicities, just plug in values into there, check your signs. You can always double check your signs. Let me just make sure, Let's plug in negative 2. That would be negative 2 times negative 5 squared times negative 1. That's going to be a negative times a positive times a positive. Let's plug in negative 0.5. Negative 0.5 times negative 3.5 squared times positive 0.5. Negative, positive, positive, negative. Okay, that works out. So it's like I kind of know that I'm doing things correct. You can always check. All right, same deal. This is f prime, I'm assuming. Yep. Okay, good. So since this is f prime, we're looking for relative extrema of f. We're doing our sign analysis of f prime to figure out when f is going up or going down. I think this is the exact same as what you had on a quiz, so maybe we're just doing it again. Zeros at 2, 3, and 4. Multiplicity of 3 is 2. Not going to change signs at 3. Multiplicity of 4 is odd, and at 2 is odd, so we will change signs. So we will change signs at 4. I know it's positive over here at 5. Positive, positive, positive. Will change signs, won't change signs, will change signs. F's going to be going up, flattening out, going down. max at 2. Going down, flattening out, going down. This is a critical point that's neither a max or a min. It's not a relative extrema. Going down, going up at 4. So max at 2, 1's good. Max at 3, not good. Max at 4, nope, that's not true. It's a min at 4, so that's bad. So it's only 1. Okay, so read your answer choices correctly. Don't just read like relative extrema. This is relative max, and x equals 4 is a min because f is going down then up at 4. All right, so we haven't seen one of these for a while where my derivative ends up being a little bit funky, and we're going to have a derivative that is going to have a denominator. Got to take the derivative of 9x to the 2/3, which means I have to take 9 and multiply by 2/3. 9 divided by 3 is 3, times 2 is 6. So I have 6x to the negative 1/3. How did I get negative 1/3? I subtracted 3/3 from 2/3. This is plus 3 minus 0 equals 0 or undefined. So that's 6 over the cubed root of x plus 3 equals 0 or undefined. F prime will be undefined at x equals 0. Why? Because if I plugged in 0, I'd have 6 over 0. That's undefined. That is a critical point. That is something we need to pay attention to. So now I have to solve this equation equal to 0. I'm going to subtract the 3. That's a 1/3. I'm going to multiply by the x to the 1/3. Divide by 3. I get x to the 1/3 equals negative 2. Cube both sides. I get x equals negative 8. Okay. So on f prime, I should be putting down negative 8 as well as 0. 0 and negative 8 are our critical points. Now, what should I plug in? And where should I plug it into? I'm going to use this f prime. This is undefined. It's a critical point. This is 0. And just kind of maybe conceptually think about things. Plug in, plug in 8. Plug in a number that you're used to. The cubed root of 8 of is 2. Positive plus 3, positive. Plug in negative 1. Cubed root of negative 1 is negative 1. Negative 6 plus 3, that's a negative. Plug in negative 27. Why negative 27? Because the cubed root of negative 27 is negative 3. So let's think about this. 6 over negative 3 plus 3. That's negative 2 plus 3, which is a positive. If I plugged in bigger values, this will get to be a smaller fraction that's negative. Add 3, it'll be positive every time. So that's my sign analysis. I have a max at negative 8. F is going up and down. Must have like a sharp point or something at 0. How many relative extrema do we have? Well, this is important to understand the difference between critical points and relative extrema. Set this equal to 0 to find your critical points. Factor out of 4x squared, x plus 3. I got 2 critical points at negative 3 and 0. However, when I do a sign analysis, I realize I don't change signs at 0, but I will change signs at negative 3, which means we only have 1 extrema. Here's where people falter. They take the derivative, they set it equal to 0, they get their 2 coordinates, they're like, great, I have 2 answers, 2 extrema. No, you don't. You only have 1. Only negative 3 is the only extrema. 0 is not. 0 is a critical point that is neither a max nor a min. Okay, 2 critical points, 1 extrema. Our first question about concavity. F being concave up. To figure out when F is concave up, you need to figure out when F prime is going up, which means you need a sign of F double prime. Sign analysis of F double prime. So This is the lesson 3 where we will blow past the first derivative, go straight to the second derivative. That has a 0, or is undefined, but I don't have to worry about it. At 2, f double prime will be positive to the right of 2, negative to the left of 2. Just use test points, plug it into 6x minus 2. If you want to factor out the 6, factor it out. That's telling me f prime goes down and goes up. It's like the same thing as our f prime to f analysis, only with one extra derivative. But the great thing about f double prime sine analysis is it not only tells me f prime going down, going up, it tells me f's curvature, f's concavity. F is concave up, concave down, and concave up. F is concave up for x is bigger than 2. Second derivative, point of inflection. A point of inflection is when our second derivative is going to change signs, either to positive and negative or negative to positive. It doesn't matter, because that is when f prime is going to change directions, increasing to decreasing, decreasing to increasing, which is f's change in concavity. So if I had a sign chart like this, I have 2 points of inflection. Just like with your first derivative, make sure you do the sign analysis. Make sure you do the sign analysis of the correct derivative. I need the second derivative, y double prime. This is just y. You have to take the derivative twice. Now, fortunately, here, there are no like fake outs. We're just going to change signs at -1. Will be positive then negative, which means y prime is going to be decreasing, increasing, which means y is concave down, concave up, which means -1 is a point of inflection. Don't just get your answer, circle it without doing your sign analysis, because there are times when you have points of no concavity that are not points of inflection, similar to critical points not being maxes or mins. Great, but that's not the answer, because the question is, what is the equation of the line tangent? This is great. So the point of inflection is here. Now I need the equation of the line tangent at this location. So like, great job. You've done a lot of work, but now let's keep going. So we got to remember how to write an equation of a tangent line. It's been a while, but it shouldn't be crazy for you. You got y minus y1 equals m x minus x1. The x coordinate is -1. Cool. The y coordinate comes from your original equation where this point is located. The slope comes from your tangent slope generator with -1 plugged in. That's the tangent slope generator generating a slope at -1. So let's find the point. Y of -1 is going to be -1 plus 3 plus 2, because -1 squared is 1. 5 minus 1 is 4. Y prime, I did it earlier, but I erased it, whatever. 3x squared plus 6x, y prime of -1 would be +3 plus -6, which is -3. All right, so I have y minus 4 equals -3, x plus 1, x minus -1. I know this is going to be the answer because it's the only one with a slope of -3. I'm going to double check that I did everything right. Distribute, add the 4. Boom. Good question. Good little review of last unit, finding equations of tangent lines, and then this unit, points of inflection. All right, since this is the second derivative, since you're asked for points of inflection, you just need to do your sign analysis of your second derivative to figure out when your first derivative is going up or going down, to figure out when f is concave up, concave down. This will be a point of inflection. Don't just assume the points of inflection are at the zeros. I have a 0 at -1, 0, and 2. I will not change signs at 2, but I will change signs at -1 and 0 based on the multiplicities. If I plugged in something like 3, positive, 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 don't change signs, change signs, change signs. F prime is going up, going down, going up, going up. Make sure you label like stuff on the left side. If you don't, some other problems are going to get tough when you're doing both at the same time. There's only 2 points of inflection where we change concavity, -1 and 0. We don't change signs of our second derivative at 2. We're not changing concavity. This is a point of no concavity, but is not a point of inflection. So -1 and 0 only. Oh, great question. This function has a point of inflection at 1, -6. What is the value of b? So the point of inflection has got to occur when the second derivative zeros are undefined. Okay? So I'm told that when x is 1, the second derivative's got to equal 0. Okay, let's see what happens. Let's find our second derivative. I got 3x squared plus 2ax plus b. That's the first derivative. Second derivative is 6x plus 2a. This has to equal 0 when x is 1, positive 1, positive 1. Okay, so plugging in 1, I get a. Great. I want to circle that, but no. The question is, what is the value of b? Well, how the heck do I find b? Well, watch this. You not only know the x coordinate, you also know the y coordinate. Go back into the original equation, y equals x cubed plus ax squared plus bx minus 4, where a is 3. So this is x cubed plus 3, x squared plus bx minus 4. Has the point 1, -6. -6 has to equal, plugging in 1 everywhere, I'll be able to find b. -6 equals 4, that's b. b is -6. 1 plus 3 minus 4 is 0. Wait. Mr. Mester made a mistake. Did you find it? Where's my mistake? -3. -3. -3. Silly Mr. Mester. -3 plus 1 is -2, minus 4 is -6. B is 0. Good question. These are challenging questions. These are more challenging than what you had on your quizzes. These are probably a little more challenging than what you're going to see on your test. But this is good review, making sure you know what you're doing. I would be redoing your quizzes, not panicking about some of these tougher problems. I make the quizzes to mimic the test, and these are, hey, examples of like possible multiple choice questions you could see. It's getting you ready for multiple choice style, but difficulty level may be different. This is a good question. This is a fine question. You're given f prime. You're looking for points of inflection on f. Now, okay, I need points of inflection. I need to take the derivative twice. No. You need a sine analysis of the second derivative, right? Positive, f prime's going up, f is concave up. But since you're already given the first derivative, you're not going to take the derivative twice. Just take the derivative once. 12x cubed minus 12, 24, 36, x squared. 0 undefined, don't have to worry about the undefined part. Factor out the 12x squared, I get x minus 12, 24, 36, 3. So for my second derivative, which I got by only taking the derivative once, because I was given the first derivative, I got 0 and 3. That's f double prime. We're not going to change signs at 0, but we will change signs at 3. Start with something like positive 4, positive, positive. Change signs at 3, don't change signs at 0. F prime going down, going up. F concave down, concave up. We have 1 point of no concavity. That's not a point of inflection. We have another point of no concavity. That is a point of inflection. 3. Good question. Ooh, this is a good one. Now we're starting to get into graphs. Okay, graphs are where like people have the most problems. So good job. All the way to 22, functions, derivatives, sign analysis. That's usually what people have no problems with. It's the graphs that people have problems with. Okay, graphs people have problems with. Let's look at this one. Okay, let's pretend I'm giving you the question. Hey, here's f prime, because guess what? Absolute x minus 2, that's what it looks like. So this is absolute x minus 2. If this is the graph of f prime, what does the graph of f look like? Here's what you have to do. You need to understand f prime signs. You need to understand f double prime signs so that you can understand the shape of f. This is lesson 4, combining lesson 2 and lesson 3. Okay, f prime signs. I'm just going to look at the y values of the graph that's given to me, f prime. They are positive until 2, where they are 0, so I have a horizontal tangent at 2, and then they're positive after 2. F double prime signs, that means f is going up, flattening out, going up. F double prime signs, you can look at either f prime increasing, decreasing, or the slopes of f prime. You can tell the slopes of f prime are negative, then positive. At 2, it's undefined. That's okay. F prime is going down, then going up. You can see that. F prime is going down, then going up. Slopes are negative, then positive. They're not 0 at 2. So f is concave down, concave up. So I need to be going up, concave down, then up, concave up. Now you're going to see there are 2 graphs like that, D and E. This is going up, concave down, up, concave up, concave down, up, concave up. How do I pick which one? Well, here's the trick. F prime at 2 is 0, which means we do have a tangent slope. It is not a situation where there's an open circle or there's like a jump on the graph of f prime. If you have an open circle, that means f prime is undefined, which means we don't have a tangent slope. When we don't have a tangent slope, we'll either have a sharp point or a discontinuity. So this graph here, f prime at 2 is undefined because there's a discontinuity. But this graph here, you can see f prime of 2 looks to be 0. So it's because of that point here, that's going to differentiate the 2 situations. That's going to give me that. That's going to give me the correct shape. That's why I select E. There are going to be a couple questions where you're given the graph of f prime. It's like, what does f look like? You got to do your lesson 4, combining 2 things. This is also lesson 4 because you're asked when is f decreasing and concave up. So I need to figure out when is f prime negative because that's when f is going down. And then I need to figure out when f double prime is positive because that's when f prime is going down, f prime is going up, which means f is concave up. I got to figure out when we overlap here. So you're going to do your analysis of your first derivative and your second. Here's your first derivative, factor out of 6, factor this. Here's my first derivative, sine analysis, focused at -1 and 2. Positive, negative, positive. Okay, so between -1 and 2, I'm decreasing. Let's look at our second derivative, 12x minus 6. Set that equal to 0. I get x equals 1/2. Add 6 divided by 12. So my second derivative, sine analysis, centers at 1/2. Positive, negative, using this, f double prime. All right. Here's where f is decreasing. Here's where f is concave up. That's when f prime is increasing. When are we doing both? Between 1/2 and 2. When is dy dx greater than 0 and d squared y dx squared less than 0? This is the graph of f. Okay. Dy dx is y prime. That's y prime is positive, which means y is going up. D squared y over dx squared is y double prime. Notation matters. You need to know that. That's when the second derivative is negative, which means y prime is decreasing, or more importantly, y is concave down. Since this is the graph of y, I need to figure out when is y going up and concave down. You need to know up, concave down looks like this. Where am I going up, concave down? Between B and C. I'm going up, concave down. Is there another interval? No, just B and C. So 2 only. Good question. Graph question. Given F, okay? Understand what you're given. Understand how you can get your answer based on what you're given. More graphs. This is good. This is good practice, you guys. If you've just stopped, or if you're like, okay, I'm good, I'm not going to do the rest of it. Like, this is where like the tricky problems come up. All the questions are about F increasing, decreasing. It's not talking about points of inflection or anything. So I just need to analyze the signs of F prime to figure out when F is going up or going down based on the signs. Now, what am I given? The graph of F prime, which means look at the y values of the graph you're given to get the signs. My y values are positive above the x-axis, negative below the x-axis. They're going to be positive until 0. They are negative until 2, where they have a 0, but whatever. Don't assume we're going up after that. It means F is going up, going down. We have a max at 0. We're decreasing from negative 1 to 1. Nope. We're increasing from negative 2 to 0. Okay, let's start from negative 2 to 0. Yeah, that's correct. F is going up from negative 2 to 0. Let's see if any of those. From 1 to 2, F is increasing. Nope. From 1 to 2, F prime is negative, which means F is decreasing. F has a local min at 0. Nope. F has a local max at 0. F is not differentiable at x equals negative 1 and 1. A lot of people might be like, oh, sharp points. It means it's not differentiable. No. F prime equals this negative y value. F double prime is going to be undefined. But F prime exists. There is a point on F prime at 1 and at negative 1. So B is the only correct answer. Graphs are what separates students on this test. This is F prime. Talking about maxes and mins, not about points of inflection. Great. So we just need to analyze the signs of F prime to figure out if F is going up or going down. Since this is F prime, look at the y's of F prime. The y's of F prime are negative until, I don't know, whatever this point is. I don't know. Then they're positive to whatever this point is. Then they're negative until whatever this point is. And then they're positive after that. So F's going to go down, go up, go down, go up. I have 2 mins, 1 max. F is going down and up twice. It's going up and down once. So 2 mins, 1 max. 1 max, 3 mins. Nope. 1 max, 2 mins. I missed it. 1 max, 2 mins. A. Let's keep going. All right, that's F double prime. I'm giving you the equation. Okay, great. When does F have a point of inflection? Okay. This is another graph problem. Understand what you have. You might be thinking, oh, points of inflection, I have to look at slopes or when this is going up or going down. Careful. I need a second derivative sine analysis. This is the second derivative. Just like the last couple questions, if I'm given what I'm looking for the signs of, just look at the y's of what you're given. It might be different from if I gave you F prime and asked you for points of inflection. Then we have to look at something else. But here we're still sticking with y's. So F double prime is positive until A, it's negative until 0, it's positive until B, it's positive after B. That tells me F prime going up, going down. More importantly, it tells me F's concavity. Points of inflection, when concavity changes, I don't change concavity at B. I just change concavity at A and 0. That's it. Okay. Now we're talking about points of inflection again. But what is given to us? F prime. This is different from the last question. Every question is different. Just treat it all different. Don't just memorize, oh, I do this when I see this. It's like that's going to just confuse you. Just understand what you need to get, understand what you have. Points of inflection are all about F double prime. The signs of F double prime, like this, which could be told by F prime going up and going down. Okay? If this is F prime, you can either look at F prime going up or going down, or you can look at the slopes, the derivatives of F prime, because the derivatives of F prime are going to be F double prime. So, F prime slopes are positive until 1. F prime is going up until 1. Boom, I got my first interval done. Then I have a 0, and then F prime slopes are negative until 2. Or you could see F prime is going down until 2. Whichever one you want to do, it works. Then we're going up again until 3. Oops, going up until 3. The slopes are positive until 3. Then we're going down until 4. Going down until 4. Or the slopes are negative slopes. And then we're going up until 5. The slopes are positive until 5. And then we're going down to 7. Not to 6, but to 7. We're going all the way down, all the way to 7. Negative slopes all the way to 7. And then up after 7. Whew. 1, 2, 3, 4, 5, 6 points of inflection. Because that's how many times F's concavity is going to change. 1, 2, 3, 4, 5, 6. E. Good question, making sure you understand what you have. Some people might be like, oh, well, isn't it just 1 at 6? 6 is the location of a max of F. That's when F prime's Y values change signs. Pay attention to what you have, what you need. All right, cool. This is like a curve sketching thing. Here is F prime. What does F look like? All right, well, we need F prime's analysis. We need F double prime's analysis. So we can kind of tell about F, its shape, what it's doing. Okay, this is F prime. So for this sine analysis, look at the Y's of F prime. Positive until -1, negative until 1, positive after that. That's telling me F going up, going down, going up. I mean, let's just look right now. Before I look at F double prime, maybe I'll double check. Going up until -1, going down until 1, going up after that. Yeah, it's got to be B. It's got to be B. Let's just make sure F double prime, which will either be slopes of F prime or F prime going up, going down. We're going down until the slopes are negative until 0. We're going up. The slopes are positive after that. That means f is concave down all the way until 0 and then concave up. So increasing concave down, decreasing concave down, point of inflection, decreasing concave up, increasing concave up. Yeah, B. Didn't even have to do the second derivative analysis. What do I have? What am I asked for? Points of inflection. That's F. Wait. So I have to look at slopes. That's just F. That's F. When does F's concavity change? You just have to look at the graph. We're concave up. Let's go blue. Concave down. Concave up. Concave down. Shit. Had that blue. Wait. No, I'm all messed up. Concave up. Concave down. Literally, by looking at the graph of F, and the graph of F's concavity is how you're going to answer the question. It's so important. Understand what you have. Understand what you're looking for. Maybe you just look at the graph. Maybe you look at the slopes of the graph. Maybe you look at the signs of the graph. It all depends. It all depends. Don't memorize what to do. Understand what you have and what you need. Concave up, concave down, concave up, concave down. Points of inflection. I have 1 point of inflection, 2 points of inflection, 3 points of inflection. Good question. All right, it might not be clear, but I'm pretty sure this means f prime of 2 is 0. F double prime is negative. What could be the graph of f? F prime of 0 does not exist or is undefined. Okay. For all x. All right, what does this tell me? F double prime is negative, F prime is decreasing, or F is concave down. I'm looking for a graph that's concave down everywhere. I'm going to start with that. No, this is concave up, then concave down. That's not it. Concave down, concave. That's not it. Concave down everywhere. Okay, maybe. Concave down everywhere. Okay, maybe. Do I have an E? Do I have an E? Concave down everywhere. Okay, maybe. So these last 3 are my maybes. F prime of 2 is 0. At 2, I have a tangent slope that's 0. Tangent slope that's 0. Tangent. Okay. Doesn't help me. F prime of 0 does not exist. Okay. F prime of 0 does not exist. No, F prime of 0 is this positive value, so that one's out. That's good. That's good as well. Sharp point or discontinuity. But what's the difference between these two? F is continuous on the closed interval from -2 to 3. Which one of these graphs is continuous, but doesn't have a derivative at 0, but has a derivative of 2 that's 0, and is concave down everywhere? This graph is continuous. Its derivative at 0 is undefined. Its derivative at 2 at 0. It's concave down everywhere. E. Okay, so read all the parts. I missed the whole continuity part. I would have just crossed this off. It's like, this isn't continuous. This doesn't. This is not an option. All right, great question. We had something like this. We're looking at f of 1, f prime of 1, f double prime of 1. I know f of 1 is 0. Why? If this is the graph of f, that we can take the derivative twice. Twice differentiable means you just can take the derivative twice. This does not mean this is the second derivative. It just means you can take the derivative twice. Think of it as a polynomial function with a degree higher than 2 or something like that. F prime, obviously f prime is some positive value. That's the slope of a tangent, right? F double prime. Well, F is concave down. If F is concave down, F prime's values must be decreasing, or more importantly, F double prime's values must be negative. So F double prime of 1 must be negative. So It looks like we're going least to greatest. The least would be the negative f double prime value. The middle would be f of 1, and the greatest would be f prime of 1. F double, f, f prime, f double, f prime, d. Okay, another one of like, here's f prime. What does f look like? Do your sign analysis at least of your first derivative, and then maybe also the second derivative. This is the graph of f prime. So look at the y's of f prime. They are negative until -2. They are positive until 2. They are negative after that. That's telling me f is going down, going up, going down. The graphs are what differentiates, guys. The graphs are the important. So I just need a graph that goes down, up, down, if that's a graph of f prime. Down, up, down. Min at -2, max at 2. If the question asks, like, when is f increasing concave down, maybe you need to be prepared to do a sign analysis of the second derivative as well. You can either look at the slopes of f prime, or you can look at f prime going up, going down. The slopes are positive, f prime is going up until 0. The slopes are negative, f prime is going down. That's telling me f is going to be concave up, concave down. Let's just double check. Going down, concave up. Going up, concave up. Going up, concave down. Going down, concave down. E. I hope I thought E was right. Down, up, down. Down, up, down. Min at -2, max at 2. I feel like I said that opposite. If I did, my bad. All right, 9 more. Here's a graph. When is dy dx and d squared y over dx squared? This is the graph of y, not y prime. Okay, so this is y. When is y prime, notation matters, and y double prime, notation matter, both negative? If y prime is negative, y is going down. If y double prime is negative, y prime is going down, which means y is concave down. When is y going down? Concave down. Going up, concave down. Going down, concave down. Going down, concave up. Derivative 0, so constant. Going up, concave up. So like constant concave up, increasing concave up. So going down, concave down, B. Charts. Understanding. F prime and F double prime are negative for which graph of F? Well, if F's negative, that means the Y's are going to be negative. I shouldn't see any of these graphs with positive Y's. Wow, E. Out. Oh, this one's bad. Okay, so E's. F prime. F prime, negative. F's got to be going down everywhere. This is not going down everywhere. This is. This is not. This is. Again, E's already gone. So D and B are my options now. D and B. F double prime is negative, which means F prime is going down, which means F is concave down. I need to be going down, concave down, underneath the x-axis everywhere. Down, concave down, underneath the x-axis everywhere. D is not that because D is like down, concave down, concave up. B. It's a good question. It's a good question. It's the same. When is y prime positive and y double prime negative? That means y needs to be going up and y needs to be concave down. When am I going up, concave down? Going up, concave down. That's it. Nope. Point of inflection. There's a point of inflection. Up, concave down, B. All right, this is good. This is like back to like a unit 2 question. graphing derivatives. All right. Good practice for unit 2. Like positive slopes, positive slopes, positive slopes, positive slopes, more positive, more positive. I mean, this makes sense. This works. Positive slopes, zero slope, negative slopes. Okay, that's not positive values, zero value, negative. That's not right. You could go backwards too if you want to. The last one, positive values, positive slopes, zero slope, negative slopes. I like this graph. Positive slopes, zero, negative. Positive values, zero, negative values. So I like 1 and 3. Um, this is not kind of like a question you're going to see. This is a unit 1 question. It's good practice. Maybe I'd ask you like if this was f prime, f double prime. Maybe that would be like a test question where it's like understanding slopes of f prime tells us f double prime values. 1 and 3. Oh, I just did it again. What was I on? Like 42 or something? I wasn't off. Like, I'm getting there. 1 and 3. Boom. E. Circle that. It's going to be right. Hey, lots of stuff going on. This is the function f. Okay, that's good. It's differentiable based on the graph. What are the values of x that satisfy the conclusion of the mean value theorem from 0 to 12? At 2, mean value theorem 0 to 12. This is back to like the first couple questions we did. 0 to 12, secant slopes and tangent slopes. So 2 and 9 have tangent slopes that are parallel to / equal to the secant slope. So 2 and 9. Yep. That's a lot of words for the answer. I don't love this question. Like, which of the following can we use the mean value theorem? It's a good little test. Like, you got to remember the mean value theorem means like the function must be differentiable. To be differentiable, you need to be continuous on your interval and also no sharp points. I hope I don't have to check. But maybe. This is not continuous at 0, so this is out. This is not continuous at 1. This is like the jump function, so that's out. This is continuous between -5 and 5. It's not continuous at 6 and -6. This is it. This is not continuous at 2 and -2 because that's when the denominator would be 0. Thankfully, I don't have to take the derivatives and check to see when that's not going to work. I can just say that one. It's continuous. I'm going to assume the derivative is also continuous on the interval. So, good question. Your function has to be differentiable. Okay. F is differentiable and decreasing. Since f is decreasing, f prime must be negative. F has 2 points of inflection. Okay. What could be f prime? If f has 2 points of inflection, f prime needs to change direction twice. That means the slopes need to change sign twice, whether it's this or the other one. And that will be our concavity changing twice. So I need f prime values to be negative. So that means if this is the graph of f prime, it needs to be below the x-axis the entire time. Okay, like the y's of f prime. But I need it to change direction. F prime needs to change direction twice. That's what we're looking for. Okay, so I'm immediately going to exclude this one because we have positive y values for f prime, which means it's f is not decreasing everywhere. So b's gone. Okay, b's gone. How many of these change direction twice? This is not changing direction. F prime is just going down. So that means f double prime is negative everywhere, which means f is concave down. That's not it. This is already out. Does this change direction twice? One time we change direction. 2 times we change direction. The slopes change. You're scared of this sharp point. Don't be scared. Don't be scared. Do you change directions? Sure. So I like this one. Let's double check. Do you change directions twice? Go down, up, down. Oh, I changed directions 3 times. 1, 2, 3 times do I change directions, which means there's 3 points in concavity, the min, the max, and the min location of f prime, which means, boom, even though it's got a sharp point, C's the right answer. This is the only one where f primes are negative and f prime's slopes change sign twice, or f prime's direction changes twice, or 3 times. 1, 2, 3 versus 4 times. 1, 2, 3, 4. That's a great question. Redo that one, definitely. Oh, this is the graph of f double prime. I love this question. Which could be the graph of f? One of these is the graph of f. Well, what information can I get from f double prime? Well, I can get f double prime signs. Just look at the y's of f double prime. They're positive until around 2. They're negative until around 5. They're positive after that. That means f prime's going down, going up. Whoa, 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 whoa. F prime's going up, going down, going up. I've done that a couple times in the last couple of days. F prime's going up, going down, going up, which is telling me F is concave up, concave down, concave up. Okay, I'm looking for a graph of F that is concave up, concave down, concave up. Concave, no. Concave down until around 2. This is, wait. That's bad. It needs to be concave up first. So I don't like that. Concave up until around 2. Concave down until around 5. Oh, I like this graph. Just based on its concavity. Concave up until around 1, then it's concave down, and then it's concave up, then it's concave down. Yeah, it's not D, it's C, right? This has the correct concavity. All I can get from a second derivative graph is the signs of the second derivative, which can tell me the concavity of F. I'm just matching concavities. Concave up until around 2, concave down until around 5, concave up. C. 2 more. Look at us. I have time to make a quiz key. Look at that. Great question. When is F both decreasing and concave down? All right. Get out our friends, F prime and F double prime, and analyze both at the same time. You'll see more of these questions on your test than you did on this review. Okay. I get x squared minus 8x minus 9. When does that equal 0? Or undefined. X minus 9, x plus 1. So negative 1, 9. That's f prime. That's when it equals 0. Positive, negative, positive. Just get it out of the way. F double prime. 2x minus 8. When does that equal 0? X equals 4. Positive, negative. That's telling me f prime is going down then up, or f is concave down then concave up. I'm going to skip the whole f prime up and down. This tells me f goes up then down then up. When is f going down and concave down? F going down and concave down between negative 1 and 4. Yeah. Last question. I did it. Oh. Oh gosh, with so many words, this has got to be so hard. It's not hard. Just read the question. F is continuous. All right, cool. It's twice differentiable. Okay, we can take the derivative twice. It means nothing more than that. Except for that 5. 5's bad. All right, cool. Where does F have a point of inflection? Is that it? Is that the question? Come on. Be better than that. Be like, what is F decreasing concave up or something like that? Point of inflection, guys. All I need to look at is the signs of F double prime, which are positive from 0 to 5, undefined at 5. I don't care. I don't care. It's continuous. So it's a sharp point or something like that. Negative from 5 to 8, where it's 0 at 8. Positive from 8 to 12, where it's 0 at 12. Positive after 12. F prime going up, going down, going up, going up. Or F, concave up, concave down, concave up, concave up. Everybody's like, this, I guess it's not. No, 5 is a point of inflection. The concavity changes. 8 is a point of inflection. The concavity changes. 12 is not, because the concavity doesn't change. It's a point of no concavity, like x to the fourth has. 5 and 8. Now, if I asked you, when are we decreasing concave up? Maybe then you'd have to put down F prime sine analysis as well. And just like make sure you got the right values and stuff like that. I did it. I'm done. Tapped out. Hope this is valuable. But do your quizzes, Definitely that fourth quiz, the quiz that you took on the review day. I'll put up a copy of it and the key after the B day. So tomorrow is Wednesday. I'll put that up on Wednesday afternoon. Make sure you redo that quiz at minimum. Make sure you know the mean value theorem. These are good practice questions. Don't memorize. Understand what you have and what you're looking for. Okay, that's the key. This unit, students have struggled on in the past. Let me just show you this at the end. I think I'll show you this in class too. Last year, and they cheated last year too. I know they cheated. Our average is 73. That's 2020, not 22. 2 years ago, 76. This was my good year. 3 years ago, 74. They didn't have homework. 73, 74, 73. Let's see. What are some of the bad scores? Somebody got 2 right. That's not good. And then 10 after that. You got to prepare yourself. The difference makers, I feel, are the graphs. Usually people can take derivatives and factor. Not everybody, though. You just got to practice, practice, practice. All right, team. I'll see you out there.